Here we were told we have a data set with n points, x1, y1, x2, y2, all the way through xn, yn. And we were told that we find the optimal simple linear regression line on that data set by minimizing mean squared error. And the corresponding intercept and slope are w0 star and w1 star. We then define this variable m to be whatever this formula is returning. And we say that sigma y is the standard deviation of the y's, so sigma y squared is the variance of the y's. And the question is, what is the relationship between m and the variance of the y's? Okay, this is the kind of question where if you try and plug in formulas, it's much more complicated than necessary. This is really a question about intuition and deeply understanding what these formulas actually tell us. So the first thing to note is that we tell you that w0 star and w1 star are the optimal intercept and slope, and they're optimal in that they're the intercept and slope that minimize mean squared error. So what I'd like you to do when thinking about a question like this is just visualize, what is this really telling me? It's saying, hey, I have some data set that may look like this. I found the line that best fits this data. And that line's slope, well, I didn't draw that super great, but that line's slope is w1 star and that line's intercept is w0 star. Okay? M is the mean squared error of that line, right? All this is computing is the sum of actual minus predicted, right? These are the predictions made by that line. This is the optimal intercept right here, the optimal slope right here. So what this is saying is for every data point in our data set, what it's doing is it's finding what the predicted output would be on that line. So it's saying for this data set, my predicted point would be here. For this point, my predicted point would be here, so on and so forth. For every one of our n data points, it's saying what is the predicted y value and what is the actual y value? How far apart are they? Square that difference and average it. That is just the mean squared error of this line. So m is the mean squared error of that line. How does this relate to the variance of the y's? Well, the thing to remember is that the variance of the y's has the formula 1 over n times the sum of yi minus y bar squared. And many students correctly noted that these formulas look similar. It's just that here there's something more complicated going on, whereas down here the value we're subtracting doesn't seem like it depends on the value of I. It's just subtracting the mean every time, whereas here we're subtracting a different prediction depending on which data point we're looking at. The connection to remember here is that the mean is the constant that minimizes mean squared error. It is the constant that minimizes mean squared error, right? And so this relates to an earlier problem on this exam where we ask you to draw the graph of mean squared error for the constant model, right? What that graph looked like was this parabola, and what we identified was at the bottom of the parabola, the vertex, its x-coordinate was the mean of the y's, and its other coordinate is the variance of the y's. Okay? And again, this is here all I'm illustrating is the fact that the mean is the best constant on the data set. And the variance is the mean squared error of that best constant. Right? You can see that these formulas are similar. I'm just using a constant for my predictions. The mean is the constant with the best predictions, but the mean squared error, right? The mean is not perfect. If I draw the mean line through this data set, it's not going to be perfect. But the variance of the y's is the mean squared error of that line's predictions. So if this line's predictions have a mean squared error of the variance of the y's, and this line has a mean squared error of m. And so when you see it this way, the question may seem a little more intuitive. What is the relationship between m and the standard deviation of the y's squared? Well, there's no way that m could be bigger than the variance of the y's because m is the mean squared error of a more powerful model than the constant model, right? The simple linear regression model has an additional level of flexibility. It can have an intercept and it can have a slope. So if the data has any correlation in it, it'll have a slope and it'll fit the data better than the best constant model will. The variance of the y's is the mean squared error of the best constant model, okay? But it's not the mean squared error of the best possible model, right? I can make many models that are better I could draw a model that goes through every single data point. That would have a better mean squared error. The variance is just the mean squared error of the best constant model, not of the best model in general. Right? So what this question is really saying is, what is the relationship between the best constant model and the best simple linear regression model? And in general, because the best simple linear regression model is more flexible than the best constant model, it can't perform worse. It could either perform the same if the data has no correlation, because the simple linear regression model could pretend to be a constant model. It could pretend to be flat. Or not pretend. It could be flat if the data had no correlation. But if it has correlation, then it'll have a slope and it'll fit the data better than the best constant model. So all of that is to say, m is less than or equal to the variance of the y's for that reason. The next subpart, which is related, says if we know that m is 0, what does that say about r, the correlation between the x's and y's? So if we're told that this thing is equal to 0, and this thing is the average of a bunch of things squared, the only way for that to be 0 is if all of these individual things are 0. Because if any one of them was bigger than 0, they can't be negative because they're being squared, but if any one of them was bigger than 0, well, then the average of them would be bigger than 0 too. So what we're saying is m is equal to 0. That means the best simple linear regression line is perfect. It makes no mistakes. It passes through every single one of the data points we have. So what this is really telling us is, imagine our data set is such that the best simple linear regression line passes through every point. So what you need to be imagining is that the data looks like this. It's possible to draw a line through every single point. So it could look like that, or the slope could be downwards, right? It could also look like, it's a weird graph here, but it could also look like that, right? Both of these are possibilities, and what we're asked for is what is the correlation coefficient r in this universe? And there are only two possible answers. Either the data set has a positive trend, in which case r is 1, which means perfect linear association. A line can go through every single data point, or it has perfect negative linear association, where it's the same condition, a line can go through every single point, but the slope is negative, whereas in the other case, the slope is positive. Okay, so that's really all there was to this one. Again, it's another type of question where if you try and work this out with algebra, it'll take way longer than you have time to do on the exam. These were meant to be quicker, more conceptual questions that you can do based on your understanding of what m actually means and what r actually means. Okay, the last two parts of this question were true and false. Okay, and the first of those true and false questions, so part C says, is it possible for there to be multiple pairs of slopes and intercepts with the mean squared error of m? The answer to that is no. And that's because the values of W0 star and W1 star are unique. Right? W1 star, we've seen several formulas for it. One of them is the correlation coefficient times the standard deviation of the y's over the standard deviation of the x's. Right? There's no way that this formula could output two different things for the same one data set. Right? It's possible for it not to be defined if all of the x's were constant, but that's different than there being multiple possibilities. Right? If it's defined, this can only ever be one thing, which means this pair of optimal slope and intercept are uniquely defined. So that's why option C, or part C, is false. But why is part D true? Like, why is it possible for there to be multiple slope-intercept pairs with the mean squared error of m plus 1? Well, there's nothing special about the plus 1 here. I could have made this plus 43 or something, as long as it was m plus something. Here, we need to remember what the graph of mean squared error for the simple linear regression model looks like. Earlier in this video, I drew the graph of mean squared error for the constant model, and that looked like a parabola in 2D. What does the graph of mean squared error look like for the simple linear regression model? Well, it's worth trying to sketch it. I mean, it's in 3D, so we're not going to be able to draw it perfectly here. But the function in particular I'm talking about is this one. And it looks like 1 over n times the sum of yi minus w0 plus, this familiar friend, perhaps from lecture, right? And in, I believe, chapter 2.3 of the course notes, if that's still the chapter number when you're watching this, we graph this function, and it looks sort of like this bowl, okay? And you imagine this is floating above us in 3D. We can walk to any point in sort of the floor we want, and that corresponds to a different combination of intercept and slope. And when we look above us, we see the mean squared error for the combination we chose. This graph has a unique minimum at the point W0 star, comma, W1 star, comma, M. But if we pick a height that's higher than M, like if we look anything higher than M, you can see there will be multiple combinations of intercepts and slopes that give us a mean squared error that is bigger than M. In fact, there will be infinitely many. If you think of this graph as being sort of like a bowl, and if you slice a bowl with a flat sheet of paper, the trace will be like a circle or ellipse type thing, meaning there will be infinitely many points that satisfy that intersection. So it's hard to see here, but imagine if this was a bowl, slice it through with a piece of paper, the intersection will be this other graph, and if you take any combination of intercept and slope that lives on that other graph, it would also have a mean squared error of m plus 1, or m plus whatever height you want. Okay, so for m, a mean squared error of m, because we were told that is the mean squared error of the best line, we know that there's only one combination of intercept and slope that got us there. For anything bigger than that, there will be infinitely many combinations. And just as a follow-up, if I said, are there multiple intercept slope pairs with a mean squared error of m minus 7? The answer is no, because there's nothing with a mean squared error of less than m, because m was the best.